Hi everyone, this is the presentation for EEL6562. My project title is Human Face Detection and Recognition. My name is Ding Yuan, and here is the introduction. My project consists of three parts. They are detect face in the given image, extract feature from facial image, and face recognition. The face detection. The first job is to detect the face area within an raw image. To detect them, I use three methods altogether. The first is to identify a face in a controlled image. The second is to identify a face by skin color, and the last one is to use Weil-Jones framework. Using skin color to identify faces has the drawbacks that skin color is not the same for all people. It can range from very light to very dark. Another disadvantage with this method is that the color of skin remains the same for the face and the rest of the body. So if the image consists of the exposed skin other than the face, the algorithm will classify that as a face, which is the undesirable. The final method is the tried and tested Weil-Jones method for detecting faces. Here's some features of this method. The features used in this method are based on the Hall wavelets. The two-dimensional representation of a Hall wavelet is a pair of adjacent rectangles, one light and one dark. To expedite the detection of Hall-like features, an integral image is used instead of working with individual pixels. To convert an image into an integral image, each pixel is made equal to the sum of all the equals above and to the left of the selected pixel. The Weil-Jones algorithm makes use of a modified version of adaptive boosting, termed Adam Boost. This is a machine learning algorithm that employs weighted combinations of weak classifier to build a strong classifier. The filters at each level are trained to classify face images that pass all the previous levels. If any one of the filters in the train fails to pass an image region, then it's immediately classified as not a face. Only those regions that pass through all the filters are classified as a face. This method is termed cascading. So I can use the Hall classifier in OpenCV or to implement it by myself. Here's some experimental results of after running my algorithm of the random chosen images and the AT&T standard database human faces. You can see that no matter which one, my algorithms exactly point out the face area, so the result is good. The feature extraction. This is the second part of my project. So before extracting the feature of a face, I will first of all consider a very important problem, that the faces are taken from different illumination conditions, which certainly will bring noise to the image at a various degree. Then the preliminary work is forced to normalize all the face images. What I have to do is to choose a common standard deviation and mean value according to the experience and most of the images in the training set. In my case, I set the mean value equals to 19 and the standard deviation equals to 70. Here's the result of my training data before normalization and after normalization. We can see that after normalization, all the pictures are under the same illumination condition. Immediately after this job is done, I will apply principal component analysis to the training set of data. I take eigenvectors and eigenvalues of the covariance matrix of the training dataset placed side by side. The eigenvectors corresponding to non-zero eigenvalues of the covariance matrix produce an orthonormal basis for the subspace. You can see the eigenvectors are sorted from high to low according to their corresponding eigenvalues. The eigenvectors associated with the largest eigenvalue is the one that reflects the greatest variance in the image. That is, the smallest eigenvalue is associated with the eigenvector that finds the least variance. They decrease in exponential fashion, meaning that roughly 90% of the total variance is contained in the first 5% to 10% of the dimensions. And in my case, I will only focus on those eigenvalues greater than 0.0001 and the corresponding eigenvectors, but neglect the remainder. Now the eigenvectors are also images, and they indeed look like faces. So let me denote omega, which describes the contribution of each eigenface in representing the facial image by treating the eigenfaces as a basis site for facial images. And here is the eigenfaces for all the human face pictures in the training set. They look indeed like faces. Also, there is a comparison between the original image and the reconstructed image. Obviously, the reconstructed image looks like the original one, and they contain the most important, which is the principal component of the image. That's the information I can use to classify it. Here's the last part of my project, that is face recognition. So it's time to recognize the unknown input image. In order to do it, I get one face from the testing data, similarly transform it into the eigenface form. Then I will compute the Euclidean distance between the projected eigenfaces of input image and each image of the training dataset. Here is some experimental result. And you can see the red line shows the minimum Euclidean distance of the input image, and for the left image, I input the human face of person 1, and the minimum value lies in the first class, that is the first 8 of the lines. And for the right image, I input a face for person 4, and the minimum value lies in the class 4. In addition, not only the minimum value, we can see from the table that the all the 8 data under the name of person 1 are much smaller than the value of the other person. And similarly for the second table, all the values under person 4 are much smaller than the other person's values. Also, I do this experiment 20 times as a unit. Here's the result of 3-unit experiment. The rate of accuracy is 85%, 80%, and 95% is really high. So now it's safe to say the classification by Euclidean distance is valid. Here's the conclusion. For the first part of the project, I detect face area within a raw input image. There may be so much background information. The features based on hair wavelets has made an improvement compared with the previous work using skin color and controlled image, which has the drawback that different people has different skin color. In addition, if I want to expedite the detection of hair-like features, an integral image is must used instead of working with individual pixels. For the face recognition job, it's the most fantastic part of my project. I get to know that some preliminary processing has to be done, like normalization, if I want to consider each image under the same illumination condition. And I set the mean value and standard deviation value according to the experience and all the images already in the training set. Finally, a good way to classify whether the input person is in the database or not is to compute the Euclidean distance and find out the minimal value, as well as the lowest class among the training set. Okay, any question? That's all. Thank you.